Hi everyone. So today the topic is about GEC basics, behavior of geotextile encased granular columns on soft deposits. Geotextile encased granular columns, often called GECs or GEC columns, are an improvement over conventional stone columns, especially for very soft or organic deposits. Where ordinary columns fail by bulging or excessive settlement, etc. Introduction. Construction on soft soil deposits such as soft clay, silts, and organic soil present significant geotechnical challenges due to their low shear strength, high compressibility, and excessive settlement under loading. These unfavorable ground conditions often necessitate ground improvement techniques to enhance bearing capacity, reduce settlement, and improve overall stability of structures such as embankments, roadways, and foundations. Granular columns, commonly known as stone columns, have been widely adopted as a ground improvement method for soft soils. They improve soil performance by reinforcing the ground, facilitating load transfer, and accelerating consolidation through enhanced drainage. However, in very soft deposits, conventional stone columns may suffer from excessive lateral deformation or bulging due to insufficient confinement provided by the surrounding soil, thereby limiting their effectiveness. And this presentation explores their design concepts, installation methods, and how they influence the performance of embankments on weak deposits, supporting critical infrastructure safely. Design principles and materials. The design of geotextile encased granular columns aims to improve the load bearing capacity and deformation behavior of soft soil deposits by providing additional lateral confinement to the granular column. Unlike conventional stone columns, the encasement allows GECs to function effectively even in extremely soft soils with undrained shear strength lower than 15 to 20 kilopascals. A fundamental design principle of GECs is a confinement mechanism where the geotextile encasement restrains lateral expansion of the granular material under vertical loading. This restraint mobilizes hoop tension in the encasement, increasing the apparent stiffness and strength of the column. As a result, axial load is transferred more efficiently from the superstructure to deeper and stronger soil layers. Another key, another key principle is load sharing between column and surrounding soil. The applied load is distributed according to the stiffness contrast between the granular column and the soft soil, commonly expressed by the stress concentration ratio. Proper column spacing and area replacement ratio is selected to ensure an optimal balance between performance and construction economy. The geotextile confines the granular core, improving load distribution and limiting lateral deformations. Selection of granular fill and geotextile properties is critical to optimize performance and durability under embankment loading. Installation techniques. The performance of geotextile encased granular columns is strongly influenced by the installation method adapted, as it affects column integrity, encasement tension, surrounding soil distributions, and overall load transfer behavior. Installation techniques are selected based on soil conditions, groundwater level, column dimensions, and project constraints. A general installation procedure is like the installation of GEC typically involves forming a vertical cavity in the soft soil, placing the geotextile encasement and filling it with granular material under controlled compaction. The encasement is usually fabricated in the form of a cylindrical sleeve which is installed either simultaneously with cavity formation or after the cavity is created. A replacement method, a borehole technique. In this replacement method, a borehole is created using augers, drilling rigs, or rotary equipment. The geotextile encasement is then inserted into the borehole, ensuring proper alignment and continuity. Granular material is placed in layers and compacted using vibro probes or tamping devices. This method is suitable for very soft soils where soil displacement methods may cause excessive ground or instability. However, care must be taken to prevent borehole collapse and damage to the encasement. Quality control and construction considerations. The quality control during installation is essential to ensure consistent column performance. This includes monitoring column vertically, encasement integrity, granular material quality, and compaction effect. Installation records typically document depth, diameter, material quantity, and installation energy. Instrumentations such as settlement plates or piezometers may be installed to monitor post construction performance. Advantages over traditional method. Geotextile encased granular columns offers several advantages over conventional ground improvement techniques, particularly when dealing with very soft or weak soil deposits. The inclusion of a geotextile encasement significantly enhances performance, reliability, uh, and applicability compared to traditional stone columns and other methods. Improved performance in very soft soils. The traditional stone columns rely on lateral confinement from surrounding soil, which is often insufficient in very soft deposits. GEC provide additional confinement through the encasement, enabling their effective use in soils with extremely low undrained shear strength, where conventional stone columns may fail due to excessive bulging. Reduced bulging and deformation. Bulging is a primary failure mechanism in traditional stone columns. The encasement significantly limits lateral deformation, particularly in the upper portion of the column where confinement is weakest. This leads to improved stability and many more predictable performance under loading. Increased reliability and predictability. The controlled confinement provided by the encasement leads to more uniform stress distribution and consistent behavior across columns. This improves design reliability and reduces uncertainties commonly associated with traditional ground improvements methods. Performance monitoring and evaluation are essential to verify the effectiveness of geotextile encased granular columns and to ensure that the improved ground meets design requirements in terms of settlement stability and load bearing capacity. Monitoring also provides valuable data for validating design assumptions and improving future projects. Object, uh, Objectives of performance monitoring. The primary objectives of monitoring GEC supported ground include assessing settlement sorry settlement behavior, evaluating load transfer mechanisms between the columns and surrounding soil, and observing the dissipation of excess pore water pressure. Monitoring helps to detect potential construction construction defects, excessive deformation, or unexpected soil behavior at the early stage. Post construction assessment. This monitoring is conducted over an extended period to assess long-term performance, including creep behavior of the textile, encasement and secondary consolidation of the subsoil. The result help to confirm the durability and reliability of the GEC system under sustained loading. Conclusion. Geotextile encased granular columns have proven to be an effective and reliable ground improvement technique for construction on soft soil deposits. By providing additional lateral confinement through a high strength geotextile encasement, GEC overcome the limitations of conventional stone columns, particularly in very soft soils where inadequate confinement leads to excessive bulging and failure. Performance monitoring and field evaluations confirm that GEC effectively reduce total and differential settlements, improve stress transfer mechanisms, and accelerate consolidation compared to traditional ground improvement method. GEC offer improved efficiency, construction flexibility, and environmental benefits, making them suitable for a wide range of geotechnical applications. Overall, geotextile encased granular columns represent a robust and economical solution for improving soft ground performance. Continued research by field monitoring and numerical modeling will further refine design methodologies and expand their application in complex soil conditions. Thank you.